we have an infinite series here. And the first thing I'd like you to try is to pause this video and see if you can express this as an infinite geometric series. And if you can express it as an infinite geometric series, see what its sum would be given an interval of convergence. So figure out over what interval of x's would your infinite geometric series converge, and what would that sum actually be. So I'm assuming you've given a go at it. So let's try to work through this together. So the first thing I want to do is let me just factor out a common factor. This might simplify it in terms of trying to express it. So let's see. If I factor out, it looks like all of these are divisible by 3x squared. So I can rewrite this as 3x squared times 1 minus x to the third power plus x to the sixth power minus x to the ninth power. And a pattern is starting to emerge. And let me actually close the brackets with the same color, with that pink right over there. And let's see, this looks like we are taking powers of x to the third. So let me write it that way. This is the same thing as 3x squared times, we could write this first term, or I guess I could say the 0th term. This is x to the third to the 0th power. Then minus, this is x to the third to the first power, and then plus, this is x to the third to the second power, and then I think you see what's going on. This is x to the third power, and of course we can keep going. But now we have to worry about the switching of signs that we keep having. So this would be -1. This is positive, which is the same thing as -1 to the 0 power. This is negative, which is -1 to the first power. So let's actually write it this way. We can write it as 3x squared times this first term. We could write it as -1, or we could just write it as negative x to the third to the 0th power. And then you're going to say plus, or plus, we could say negative x to the third to the first power. -1 to the first power is -1. X to the third to the first power is x to the third. Plus negative x to the third to the second power. Plus negative x to the third to the third power. That's this term right over here. -1 to the third power is -1. And of course, x to the third is x to the ninth. And it keeps going. And so this makes it a lot clearer what our common ratio is. Our common ratio here is negative x to the third. And over what interval would this converge? Well, it's going to converge if the absolute value of our common ratio is less than 1. So we're going to converge if the absolute value of our common ratio, which is negative x to the third, is less than 1. Or another way of saying this is the same thing. The absolute value of a negative is going to be the same thing as the absolute value of a positive. So that's the same way of saying the absolute value of x to the third is less than 1. Or saying that x to the third is less than 1 and is greater than -1. And the way that's going to happen, if you take the cube roots of both sides of this, or all the sides of this inequality, you're going to get that x is going to be between -1 and 1. This right over here is our interval of convergence. Interval of convergence. And if we restrict our x's to that, what is this going to sum to? Well, this infinite geometric series, our common ratio, its absolute value is less than 1. And so this is going to be equal to our first term, I guess we could say, or the thing that's multiplying by this whole thing. But if you multiply it out, this would be our first term. Is going to be 3x squared, all of that over 1 minus our common ratio. So 1 minus negative x to the third, well, that's just going to be 1 plus x to the third. So everything we've done so far is we've shown that this, let me actually write it this way, that this thing is equal to this thing over the interval of convergence. So let me write the copy and paste it. So right like that. Over the interval of convergence, if x is between -1 and 1, these two things are the same. Now, we can start to put our calculus hat on here because this looks interesting. This, you might remember, this looks like the derivative of something that's familiar. 1 plus x to the third, what's the derivative of that? Well, that's 3x squared. So it looks like this right over here is the derivative of the natural log of 1 plus x to the third, or the absolute value of 1 plus x to the third. And if you don't believe me, let's take the antiderivative of this thing right over here. In fact, for fun, let's take the antiderivative of both sides of this. And if we do that, then we will have shown essentially a geometric series representation of whatever the antiderivative of this thing is. So I encourage you to pause the video again and try to take the antiderivative of both sides of this equation. So we're going to take the antiderivative of the left-hand side, and we're going to take the antiderivative of the right-hand side. Now on the left-hand side, I mentioned that, hey, it looks like we have an expression and its derivative that just calls out for u substitution. So if we say that u is equal to 1 plus x to the third, let me write this down. So u is equal to 1 plus x to the third, then what's du going to be? So then du is going to be equal to 3x squared dx. So notice we have u, and then du is this right over here. So this expression right over here could be rewritten as, so let me go over here. This could be rewritten as the integral of du over u, or I could say let me write it as 1 over u du, 1 over u du, which of course is going to be equal to the natural log of the absolute value of u, the natural log of the absolute value of u plus some constant. And we of course know that u is 1 plus x to the third. So this is going to be equal to the natural log of the absolute value of 1 plus x to the third, 1 plus x to the third plus c. Now, we're restricting our domain for x being between -1 and 1. So for that domain, this thing is always going to be positive. So what we can do, we don't have to write the absolute value sign. So this is going to be equal to the natural log, let me write it, the natural log of 1 plus x to the third, 1 plus x to the third plus c. So that's this left-hand side. And the right-hand side's actually a lot more straightforward. This is just a straightforward polynomial. Now, as you can imagine, we're going to get a plus some type of constant there. So let me differentiate them a little bit. Let me call this one c1. And then on the right-hand side, what do we get? The antiderivative of this is going to be, let's see, the antiderivative of x squared is x to the third divided by 3. So this first term, the antiderivative is just going to be x to the third power. The derivative of x to the third is 3x squared. Now, this term right over here, negative 3x to the fifth. The antiderivative of x to the fifth is x to the sixth over 6. X to the sixth over 6, but then we have that 3 over here. 3 over 6 is 2. So it's negative x to the sixth over 2. Actually, let me do that in a different color just so we can keep track of it. So this one right over here is negative, the antiderivative is negative x to the sixth over 2. And then, let's see, I'm running out of colors. The antiderivative of x to the eighth is x to the ninth over 9. So it's going to be plus x to the ninth. And then we have this 3. 3 over 9 is 3. And I think you see a pattern happening. And then, let's just do one more of these for fun. X to the 12th over 12, but we have this 3. So negative x to the 12th over 4. And then we keep going. And then we're, of course, going to have some constant. And actually, let me put the constant in the front. So let me copy and paste that, or cut and paste that. So I have some space. So let me right over here, I'll put some other constant, c2, it doesn't have to be the same one, plus all of this. Now to simplify this, I could subtract c1 from both sides, or essentially from c2, and then I'm going to have the natural log of 1 plus x to the third power. 1 plus x to the third power. And this is kind of neat, what we've just done with a little bit of integration, is equal to c2 minus c1. Well, this is some constant minus some other constant, so that's just going to be some arbitrary constant, plus all of this business, And we can even figure out what the constant is going to be by trying out some values of x that's in our restricted domain. Well, x equals 0 is between -1 and 1, so let's see what happens when x is equal to 0 to solve for c. If x is equal to 0, we get natural log of 1 is equal to c plus, well, all of these terms are going to be 0. 0 to the third power minus 0 to the sixth, on and on and on, plus 0, plus 0. Or another way, and natural log of 1, of course, e to the what power is 1? Well, that's 0. So c must be 0. C is equal to 0. So this thing right over here is equal to 0. So what we've just done, using a little bit of integration, is starting with let's just appreciate what went on. Starting with an arbitrary infinite series, we showed it could be represented as a geometric series. We defined an interval of convergence over which this would converge, over which the common ratio's absolute value is less than 1. And then using that, we expressed its sum. And then we took the antiderivative of both sides to figure out an expansion for the natural log of 1 plus x to the third power, which, so at least in my mind, that was pretty neat. This is what natural log of 1 plus x to the third power is x to the third power minus x to the sixth over 2 plus x to the ninth over 3. So on and on and on. And actually, let's just to kind of give ourselves some closure here, let's write it in sigma notation. So we could write the natural log of 1 plus x to the third, 1 plus x to the third, over our restricted domain where the absolute value of x is less than 1, is equal to the sum from, let's say n equals 1 to infinity of x to the third to the nth power, so to the first power, the second power, third power, over n. This is x to the third over 1, x to the third squared over 2. Oh, and I, of course, have to throw in, let's see, this first one is, we're going to have to care about the sign, so let me throw in a -1. Let's see, -1 to the first power should be negative, but here it's positive, so I'll say -1 to the n plus 1, -1 to the n plus 1 power. Does that work? I think it does. When n is equal to 1, this thing just becomes 1. This is x to the third over 1. When n is equal to 2, this becomes negative, which it needs to be, and then this becomes x to the sixth, and we're over 2. And so there you go. We are done. I found that pretty satisfying.